Delta H of reaction values, they come from experimental data. And the way that we determine those values, the experiments that measure heat exchange are called calorimetry experiments. And the measurement device is called a calorimeter. So you guys are going to learn more about calorimetry in lab in our last week of lab in experiment 12. There are two main types of calorimetry experiments. Constant pressure calorimetry, which is also called coffee cup calorimetry, or constant volume calorimetry, which is called bomb calorimetry. It has nothing to do with bombs that are destructive and can hurt people. It's just the name for constant volume calorimetry experiments. So we're going to talk about constant pressure first. Constant pressure calorimetry, the heat that is released or absorbed during a chemical reaction, is measured under conditions, obviously, of constant pressure. What this usually means is that the reaction vessel is open to the atmosphere. So air comes in, air comes out. The pressure outside is the same as the pressure inside. Constant pressure. Under these conditions, Q, or the heat that is released or absorbed in the chemical reaction, we can say that it's equal to delta H of reaction. We don't have to worry about any work in this system. So we're going to talk about coffee cup calorimetry. This is what you'll see in experiment 12. We don't do bomb calorimetry in general chemistry. We do coffee cup calorimetry. So in coffee cup calorimetry, the reaction vessel consists of two nested styrofoam cups, coffee cups, that are covered with a lid. So there's a picture of it down here. You have one styrofoam coffee cup inside of another styrofoam coffee cup to try and increase the insulation of our calorimeter. Then you put a cardboard or styrofoam lid on top and stick a thermometer in so that you can measure the temperature change in your system. Most coffee cup calorimetry experiments involve water as the solvent, and they have something to stir the reaction. So what we would use in our lab is something called a magnetic star. You put it in the bottom of your coffee cup calorimeter, and we put that on something called a magnetic stir plate. So the magnetic stir bar is spun using the magnetic stir plate, and you can control the speed of the spinning. And that ensures that there's thorough mixing of your reaction that's going on in the solvent in your calorimeter. All right, so the system consists of chemicals that are undergoing their change. So this could be two chemicals reacting, or it could be a chemical dissolving in the water, which is not quite a reaction, as we learned back in chapter 1. That's just a physical change, dissolution. But the system is the chemicals undergoing the change, and the surroundings consist of the contents of the calorimeter, which is usually water, a solution of water, the calorimeter itself, which are your coffee cups, and any materials around the calorimeter if your calorimeter isn't very good and the heat can escape. We usually assume that the calorimeter creates an isolated system. So in experiment 12, you'll see what happens if you don't assume this. You have to measure the success of your calorimeter experimentally. But typically in class, we're going to assume that the calorimeter creates an isolated system and that none of the heat escapes from the calorimeter. So we only have to worry about the temperature change inside of the cup. We only have to worry about the temperature change of the solution. So Q of the surroundings is just going to involve the solution inside of the coffee cup, not any temperature change of the coffee cup itself or any temperature change of the area outside of the coffee cup, only the solution. So Q surroundings we calculate with this formula. Q surroundings is equal to the mass of the solution times the heat capacity of the solution times the change in temperature. This is the same as our equation we had before that was used to calculate the heat capacity, where we had C equals Q over M delta T. Now we've moved it around, so we're solving for Q. So Q equals M delta T times C, our heat capacity of the solution. Because we learned this earlier, the system and the surroundings, there's nothing else outside of the system and the surroundings, so their total energy has to be zero. There is no heat that's lost or created in our reaction, so we can't have anything other than zero when we add together our system and our surroundings. The heat that is transferred between the two doesn't go anywhere else. So the heat that is given from one enters the other, and they add up to zero. So because the enthalpy change for a chemical process taking place in a coffee cup calorimeter, our delta H of reaction, which we said is equal to our Q for the reaction, is also equal to the negative Q, or the negative heat of the surroundings. So the heat of the reaction is equal to whatever heat is lost from the surroundings, or whatever heat is gained from the surroundings is equal to the heat that is lost from the reaction. So this is what that looks like. That's what our sign convention tells us. So for an exothermic reaction, our exothermic, the heat is leaving the system, so we have negative Q of system, and we have negative delta H of the reaction. When it leaves the system, it enters the surroundings, so we have positive Q of surroundings, and a temperature increase in our solution, which is our surroundings. For an endothermic reaction, we have heat going into the system, so it's a positive Q system and a positive delta H of reaction. When the heat goes into the system, it's leaving the surroundings, so we have a negative Q, and the temperature of the surroundings decreases, so we have a negative delta T. And one common application of coffee cup calorimetry that we're going to discuss a little bit in our example problem is determining delta H of our dissolution, so the change in enthalpy for a dissolution reaction, so when something dissolves. So here's our example. We have 2.96 grams of ammonium perchlorate dissolved 106 grams of water, and the temperature of the solution is decreasing from 25 to 23.04 degrees Celsius. We want to calculate the enthalpy of dissolution for ammonium perchlorate. So what we do here is we want to find, so first what we know the temperature change, we know the mass of our solution, and we know the specific heat of water, so which is also the specific heat of our solution, because the ammonium perchlorate doesn't affect the specific heat very much. So we can find Q of our surroundings, which is the same as Q of our solution. So all of the water and all of our water and the ammonium perchlorate that's dissolved in it. So that is our surroundings. Our system is the reaction itself. So just the reaction, none of the solution involved in the reaction. So for our Q surroundings, or our Q solution, it's going to be equal to our mass. So our mass is going to be the mass of the total solution, which is 100 106.00 plus 2.96 grams. So we have to add the mass of our solvent and the mass of our solute to get the mass of our solution. So that's 108.96 grams. And we want to multiply by our specific heat, which is 4.184 joules per degree Celsius. And we want to multiply by our change in temperature. So we had an initial temperature of 25 and a final temperature of 23.04 degrees Celsius. So our grams cancel out, our degrees Celsius cancels out, and we end up with joules. So our Q surroundings, or Q of solution, is going to be equal to negative 894 joules. All right, so it's negative because our temperature decreased, and we're still talking about the surroundings. All right, so we know that Q of the system, or Q of the reaction, is going to be equal to negative Q of the surroundings. So whatever heat is lost by the reaction is gained by the surroundings, and vice versa. So that means that Q of our reaction is going to be positive 894 joules. We have to multiply this by negative 1. So now we have our Q of our reaction. And the last thing we need to do is find out how many moles were involved in this reaction. So I'm going to erase and start with a clean slate. So we had 894 joules. We'll keep that in mind. That's our Q system. All right, so now we want to find the moles so that we can end up in kilojoules per mole. All right, so we have 2.96 grams of our ammonium perchlorate. And we're going to divide by the molar mass to get moles. So the molar mass, I looked it up, was about 117.49 grams per mole. So we put the grams on the bottom so that they cancel out, and we end up with 0.0252 moles. And our last step is to go our Q system and divide by moles so we can get joules per mole, or convert to kilojoules per mole. So 894 joules divided by 0.0252 moles is going to give us, I'm going to convert to kilojoules. So I'm going to do this, and then, so this is going to be 35,500 joules per mole. And to our answer in kilojoules, we're going to move our decimal place 3 times over. So we have to divide by 1,000 to go to kilojoules. So 35.5 kilojoules per mole. And this is going to be positive. The way that I can tell that is that our Q system was positive. The other way I can tell that, if you lose track of your signs throughout the process, is to look back at our problem. So our problem tells us that the temperature of the solution decreased. So if the temperature of the solution decreased, that means that delta T is negative, and Q surroundings is negative, which is what we saw. So Q system is positive, and delta H should be positive, which is what we got. All right, cool. So these are the steps that I just followed. First, want to use the mass and the specific heat of the solution, which is mostly water. And then you want to find, so you want to use the change in temperature with the mass and the specific heat to find the heat change or energy change of the surroundings or the solution. So that's Q of the surroundings. Next, you want to plug it in, as in just make it negative to find Q system. You want to calculate the moles of reactant from the known mass in the problem and divide the Q system by those moles to get your answer in joules or kilojoules per. Cool. So you can use these steps if you get a little confused on how to solve these constant pressure calorimetry problems. Another example that was shown is pretty cool, something you could theoretically do at home, though you want to be very, very careful if you did decide to try this. As shown in your MindStep modules, you can use the properties of heat transfer to estimate the temperature inside of your fireplace. So the first step, there's a little video that shows this. The first step is to put your steel bar in the fire and let it heat up. Your second step was to measure the mass of your water and take the initial temperature of your water, step 3. Step 4, you remove the steel from the fire and add it quickly to the water. So this is my little steel bar in my water. Add it quickly to the water and seal the lid so that no heat can escape, at least through the top of your cup. And then you're going to want to stir. So you could use your thermometer to stir if you have a thermometer sticking out of here. Or if you're fancy, you can have a magnetic stir bar. Or if you have a really good thermos, you can probably just stir it by kicking it around, like swirling it carefully in your hand. Anyway, so you want to stir it, and then you're going to record the highest temperature that your thermometer gets to, the highest temperature of the water, as your T final. So if you did that with the numbers that I gave you here, you would want to plug all of that in. So you'd have 100 grams times our specific heat of water, 4.184 joules per gram degrees Celsius, times our temperature change, which is 20 degrees Celsius. So the heat that is produced by putting the steel into your cup of water gives you 8,400 joules. And that heat is going to be the same as what you have in your, that heat is the same as what was lost from the steel. So I'm going to rewrite that using what we learned from last time with specific heat. So the specific heat of steel is 0.42 joules per gram degrees Celsius. I looked it up on Google. And that is going to be equal to the Q that we just calculated. So 8,400 joules. And that's going to be over our mass of our steel, which I'm going to say is about 25 grams. These numbers might not work in real life, but it's showing you how you would do it if you wanted to. So our final temperature is the same as the final temperature of the water. We plug that in. So we would divide 8,400 by 0.42 joules gram per Celsius, and divide also by our 25 grams, or sorry, yeah, 25 grams. So joules will cancel out, grams will cancel out, and we'll end up with our degrees Celsius. And our final degrees Celsius will be about 800 degrees Celsius, which is about the temperature of a pretty cool fire, to be honest, a pretty red hot fire. So that's how you would plug that in. So you want to use the Q that you got from your water to determine your initial temperature. So your X is your initial temperature of the steel, which is approximately the same as your initial temperature of your fire, which I found to be 800 degrees Celsius. So this is a pretty cool real life example. All right, so finally, we're going to talk a little bit about the kind of calorimetry you will not see in the lab. So this is our constant volume calorimetry, or BOM calorimetry. Up to now, we assumed that no heat was transferred to the calorimeter or to the outside surroundings. But that's not really true. As you'll see in experiment 12, we actually calculate how much heat was transferred to the calorimeter. So we don't even assume it in our lab. But if you want to be really precise and not assume that ever, you need to use constant volume calorimetry. And these are best used for combustion reactions that produce a lot of heat. So these reactions that produce a lot of heat, you don't want to try them in a constant pressure calorimeter. You don't want to try them in a coffee cup because they will probably melt your coffee cup and cause a lot of damage. So we want to try them in what's called a BOM calorimeter. When we do these reactions, they take place inside a sealed steel vessel called the BOM. So this is the BOM in our figure. It's this little chamber that we have our reaction happening in. So inside of the BOM is our little sample that is on fire because this is a combustion reaction. Outside of the BOM is a bath of water. So we've got water completely encasing our BOM. And then outside of the water, we have an insulated chamber, so an insulated jacket. So we've got several layers of protection here. So we've got our insulated jacket, our water, our steel BOM, and then our reaction. The temperature change of the chemical reaction is determined by measuring the temperature change of the water that is surrounding the BOM. So we're not too worried about the heat escaping the BOM. We're okay with that. We know how much heat is released from the BOM itself. We know the heat capacity of the steel, so we know how much the water temperature should be changing relative to the reaction. So, because the reaction takes place in a sealed BOM, we call this constant volume calorimetry. It's constant volume because nothing is escaping our sealed BOM, unlike our coffee cup where air could clearly escape. We didn't have a crazy amount of pressure where our system would explode. In this case, we do have a crazy amount of pressure inside a sealed BOM, which is why we call it BOM calorimetry. So in this calorimetry experiment, under constant volume conditions, we can't actually say that Q system is equal to delta H. It's actually equal to delta E, which was our internal energy back from the beginning of this chapter. However, the difference between delta E and delta H is quite small for most reactions, so we can sort of still say that it's the same, which we'll do in this section. And won't matter too much outside of the lecture because we aren't going to be practicing BOM calorimetry in general chemistry. So our equations are pretty similar. The heat that's released in the combustion reaction from the reaction or from the system, our Q system, is absorbed by the BOM and the water. So our surroundings in this case are both the BOM and the water. So we know that some of the heat escapes the BOM, but we're hoping because of the insulation that most of the heat doesn't escape the water. So this is our Q surroundings. So just like before, Q systems plus Q surroundings equals 0. Or Q system is equal to negative Q surroundings. All right, so the heat that's absorbed by the steel BOM is calculated by the temperature change of the water bath and the BOM heat capacity. So this is a constant for our steel chamber. It's the heat capacity of the BOM, C BOM. The heat that is absorbed by the water bath is calculated the same way we did it before. The mass of the water, the specific water, and the temperature change. So let's practice. We have a 0.430 gram sample of this molecule, bisphenol, and it's being burned inside of a bomb calorimeter. Our temperature is increasing, the water temperature, that is increasing from 24.4 degrees Celsius to 27.1 degrees Celsius. So our delta T is going to be 27.1 minus 24.4 degrees Celsius. Our calorimeter contains 1.14 times 10 to the third grams of water, and our bomb has a heat capacity of 846 joules per degree Celsius. So we want to calculate delta E for the combustion reaction. All right, so let's see here. We've got delta T equal to 27.1 minus 24.4. So our delta T is 2.7 degrees Celsius. So our Q of water, we're going to calculate first, is equal to our mass of water, so 1.14 times 10 to the third grams, times our heat capacity of water is 4.184 joules per gram degrees Celsius, times our temperature difference, which is 2.7 degrees Celsius. So Q water is going to be 12,878 kilojoules. And now we want to find Q bomb to finish off our surroundings. So Q bomb is going to be equal to our heat capacity, our bomb heat capacity, which is 846 joules per degree Celsius, times our temperature change, which is the same as our temperature change for water, so 2.7 degrees Celsius. And that is going to be 2,284. Sorry, that was joules, not kilojoules. Joules. So I like to put everything in kilojoules. So we're going to move our decimal place over 3 and say 12.878 kilojoules and 2.284 kilojoules. All right, so our Q system, once again, is equal to negative of Q surroundings. So that's going to be equal to negative 12.878 kilojoules plus 284 kilojoules. So our Q water and our Q bomb make up our surroundings. All right, so our Q system is going to be equal to negative 15.162 kilojoules. All right, so there's our Q system. So I'm going to erase. So Q system is equal to negative 15.162 kilojoules. So that is for this system. That's not for the reaction. So to get Q system for the reaction, we need to consider how much of our reactants we started with. So we have 0.43 grams of bisphenol. Bisphenol A, to be precise. And I looked up the molar mass of bisphenol, and it is 228.16 grams per mole, And we want grams on the bottom that we can end up with moles. So our moles are 0.00188 moles of our bisphenol A. So now we have Q system and we have our moles. So we just need to divide to find the change in energy for the reaction. So our answer, our delta E for the combustion reaction is going to be negative 8,065 kilojoules per mole. And in our balanced reaction of bisphenol combustion, there's only 1 mole of bisphenol. So you don't need to worry about that. But if you wanted delta E without the per mole part, you would look at your balanced reaction. But I'm just going to leave it in kilojoules per mole. So 8,065 kilojoules of energy are released during this combustion reaction. Like all other combustion reactions, it is exothermic, and we have a release of energy. And here are those steps again if you need some help with these problems. Very similar to the steps for constant pressure calorimetry, but this time you need to look at the water and the bomb to get your surroundings, which are the water plus the bomb. All right, so that's it, 10.4. Have a good night, guys.